Our next lesson is going to be dealing with permutations, when all objects are distinguishable. Now, a natural question might be, when are objects not distinguishable? But basically, your objects are going to be different from each other. If that makes any sense? So we won't have any repeating letters, etc. So if order matters in accounting, then it's a permutation. So last time we took a look at this permutation and 9p4. Now 9p4 is going to be 9 factorial divided by 4 factorial, open brackets 9 minus 4 factorial. And we can know that simply from NPR is going to be n factorial divided by r factorial n minus r factorial. If you are using your calculator to calculate this, I would even put extra brackets around the denominator, just to make sure that we're calculating it correctly. So using factorial notation, and when we do that, what we can get is 9p4 is equal to 9 factorial divided by 4 factorial, and 9 minus 4 is 5 factorial. And when I do this, what I get in my calculator is 3024. So you can use this on your calculator, so 9p4. So I believe I have up and running on a different website. I'm just going to calculate 9p4, and the website that I'm going to use is going to be an emulator for the TI. So I'm just going to hit the math button, and the math button is on the left-hand side. So when I hit the math button, it opens up this menu. Now, what I would like, if you look at the top banner, there's math, num, complex, probability, and fraction. So I'm just going to scroll over to probability. And when we see probability there, the numbered options at number 2 is NPR. So I'm just going to either scroll down and highlight number 2 and hit enter. And this is where my calculator opens, and I believe I'm trying to calculate 9p4, 3024. Different calculators will be different. So let me look at example number 2. Consider the letters in the word sandwich. So instantly what I did is I just wrote sandwich backwards. I looked for letters that repeat, and there was no matching letters that repeat. So in other words, all the objects are distinguishable. So how many different 5-letter words are possible? Now these are mathematical words. We're just going to put 5 different letters together. Order matters here though, and simply because, now you may be, well, when would order not matter? So CIW is different than WIC. So the order of the letters will change things. So that's what we mean with order matters or placement matters. So how many different 5-letter words are possible? What I'm going to do here is I'm going to use the fundamental counting principle, because that is what is most natural to me anyways. So I recognize that I have 8 different objects. I have 5 places to put them. So for my first option, I'm going to have 8 letters, and you can say check mark to the H or whatever. And then I have 7 letters, and then I have 6 letters, and then I have 5 letters, and then I have 4 letters. And then there are no other places to put my letters. So essentially, I'm only picking a subset of all possible elements, or I'm placing a subset of all possible elements. And if I was to write this in permutation, so I would be like, well, there's 8 or distinguishable objects. And I'm going to place, how many? 5 of them. So it would be 8p5. So 8p5, I punch that into my calculator, I get 6,720. Okay, so now I'm going to go to the next example. How many different 6-letter words? Well, here there are 6 different decisions. Pardon me. There are 6 different decisions. I have to put what letter comes first, second, third, fourth, fifth, and sixth. And if I take a look, how many options are available if I have 8 letters? Well, there is 8. And once I put 1 letter in, well, then there is 7. And then there are 6. 5, 4, 3. And at a certain point, you're like, I'm sort of getting this fundamental counting principle down, but we could also use permutations. So out of 8 elements, I'm going to place 6 of them. And 8p6 is 20,160. Now, to go from the first example where there's 5 letters to 6 letters, really what we're missing is a factor of 3 that we multiplied to. But regardless, great work. Now, example number 3, Kelsey has downloaded 10 songs from an online store. I find this question really confusing because I don't know why it just doesn't mesh with my brain. So I'm just going to call these songs A, B, C, D, E, F, G, H, I, J. Those are the first 10 letters, and there's nothing significant about these. They're just songs. So Kelsey has downloaded 10 new songs from the online music store. She wants to create a playlist using 6 of these songs arranged in any order. How many different 6-song playlists can be created from her new downloaded songs? I think what gets me is she wants, it's right here, I'll highlight here, she wants to create a playlist using 6 songs arranged. I'm going to take out in any order. That part of it has always confused me. So we are looking for a playlist of 6 songs. One would think that the order would matter when we're choosing songs. So if I'm choosing 6 songs, here it is. I have 10 songs to choose from. So I'm going to jump straight to the fundamental counting principle. That's where I'm most comfortable. So what's my first song? Well, I have 10 options for that. Second song, I would presume that we're not going to double play these, right? Because that would be kind of ridiculous. And then I have 9 songs left, and then I'm going to have 8 songs, okay? And then I'm going to have 7 songs, and then I'm going to have 6 songs, and then I'm going to have 5 songs. So that is how many different arrangements or different playlists that I can make. I made 2 assumptions. That order does matter. That is the first song. If Billie Jean is the first song, then that it will be different playlist than if Billie Jean's the second song. Anyways, I'm just going to do the math. I'm a math teacher, not a music critic here, so I'm just going to punch this in. Okay, and I believe this is going to be 151,200. So that's from the fundamental counting principle. But this is a permutation. We're only taking a subset of the total elements, and we're going to arrange them in an order. So from 10 elements, I'm going to pick and place 6 of them, 10p6. And if I calculate 10p6, it is 151,200. So we can often use permutation notation Or we can also use the fundamental counting principle, going back and forth. Now, a permutation, order matters. Are you placing them? And maybe, since in the notation that we're using here, placing maybe stands for P. It doesn't, but it can definitely help us out.